Alright, so today we're going to start chapter 4. You're going to need the last little handout and just to cut out this scatter plot looking thing here for today's notes. Alright, let me see if I can focus. Blurry. Okay. So you'll definitely want to pause today's video. We're going to have kind of some tables that take a while to fill out. So I'm going to fill them in kind of quickly, and what you might want to do is just wait for me to finish filling out the table and then pause it and then write it all in. So we're going to talk about correlation, which is something that describes how two variables are related to each other. And more specifically, not only it talks about whether they have a relationship, but how strong that relationship is. So you should have done scatter plots maybe back in Algebra 1 or something. But real data hardly ever falls perfectly on a line. So a lot of times we're going to have a scatter plot like this. Okay, so let's just take a look at these. So I do want you to kind of tape that in your notes. So notice both of these have a linear pattern. It's not a perfect line, but you could kind of draw a line of best fit in between all of these. So this is a positive linear since it goes up. This is a negative linear. This is what's known as a weak linear because notice it's just a little bit too spread out, but it's still technically linear. It just wouldn't be as strong. And then this would be non-linear because it actually has a curve to it, and same with this. Okay, but this would be positive nonlinear and this would be negative nonlinear. So certainly the information doesn't have to have a linear relationship, but we're going to focus on those that do have a linear relationship because those are easier to talk about. So we're going to find a quantity called the correlation coefficient. And this is exactly what I was mentioning before. This is a measure of the strength of the linear relationship. So correlation coefficient is only used when you do have a scatter plot that looks linear. Otherwise, we don't even talk about the correlation coefficient at all. So we call the correlation coefficient, we use the letter R. And so the correlation coefficient, this is a double-sided inequality, and all that means is it's going to be something in between -1 and 1. You can't have any outliers. So if you're going to talk about a correlation coefficient, you can't have like a straggled point over here, like hanging out right here or something. So if there are outliers, then it's not appropriate to even talk about the correlation coefficient. So let's look at the formula, and then we're just going to realize that this is kind of a tedious formula, but we're going to be able to do it. It's not that hard. Okay. So R, which is the correlation coefficient, is going to be 1 minus 1, 1 over n minus 1 rather. And then the sum of all the x values minus the averages over the standard deviations times the y minus the y average over the y standard deviations. Okay, so just to kind of remind you, the x bar is going to be the average of the x's in the sample. Remember, we use mu when it's an overall population average. So y bar will be the average of the y's in the sample. S with a subscript of x will be the standard deviation of the x's in the sample. Remember, if it were a population, it would be sigma, not s. And then finally, S sub y is the standard deviation of the y's. So you are definitely going to need your calculator today. Like I said, what we're doing isn't really that hard, but it is a little tedious. Okay, there's a lot of numbers to kind of keep straight. So we're going to try to kind of keep this condensed here. So let's say I want you to compute the correlation coefficient. In other words, tell me how strongly related X and Y are. If these are the X and Y values. All right, so over here, I'm going to create a table. Now the table is purely for organization. So you're gonna want to write kind of small here, okay? But we want an X, we have our Y, and then what we're gonna do is we're just gonna find the pieces of this problem. So first I'm gonna find the X minus X bars over the standard deviation of the X's. I'm gonna do the same for the Y's. And then finally, I'm going to find their product. All right, so first I'm going to write all the values. So you should be able to make a decent table because you have notebook paper. All right, so I'm going to get rid of these lines because in the end we want the total or the sum of these things anyway. So now I'll have room to actually do that. Okay, the first thing I'm going to need to do though is I'm going to need to find all of these things. I'm going to need to find the average of the X's, the average of the Y's, the standard deviation of the X's, and the standard deviation of the Y's. So again, I'm going to try to kind of squeeze this in. So the X bar would be the sum of the X's over 5. So I'm definitely not going to spend too much time on that. You should know how to take the mean. The Y bar is going to be the same, the sum of the Y's divided by 5. So if you work those out, it's 3.4. Okay, the standard deviations are going to take you a little bit of time, but I'm going to briefly remind you how to do that. Okay, for standard deviation, you take the square root of every value minus its average squared and you add them up. So I'm going to say dot, dot, dot. And then over n minus 1. So I'm going to tell you what that is in a minute, but for the Y's, you do the same. Just remember that when you change, you need to change over to all the Y values. So it's Y value minus the Y average squared plus next Y value minus that average squared plus dot, 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 and then all over 5 minus 1. Okay, so I'm not spending time finding standard deviation because we've already done this, okay? But I am going to take it out to a lot of decimal places. So I'm going to take it out to 6 decimal places, and you'll probably want to do this on your homework as well. So you might want to pause the video and make sure that you can still remember how to do standard deviation and make sure you can get those answers. All right, so now you're going to take your calculator. I don't have my scientific one, but this one will work. And you're going to do exactly what this says, value minus average over standard deviation, and you're going to write the result right here. Okay, so I'm just going to do the first one, and then we're going to fill all the rest of them in. So it's 1 minus the average of the X's, which was 3, and then over the standard deviation of the X's, which was 1.581139. Okay, notice you do get a negative value, and so you're going to do that kind of over and over. Make sure that you're really, really careful here. This one's 0 because the mean and the X value are actually the same. So that's kind of a nice change. So I'd really rather you not just copy the numbers from the table, actually pause it and see if you can figure them out. We're going to do the same for the y's. So I'll show you the first one, and then again, I'm just going to write them all down. So it's first y value, which is 2, minus the average of the y's, which is 3.4, and then divided by the standard deviation of those y's, which was 2.302173. And you're going to do the same thing. So negative 0.6082121. So the point of this table is kind of like the tables have been in the past. It's just purely organizational. Frankly, this is way too tedious of a formula to try to do without some sort of organization. And that's not a challenge for you to try to do it. It's just really, really ugly. Okay. So these are the hardest ones to figure out. Now this is just take these two and multiply them together. So if I do that here, then I'll get the following. Notice 0 times anything is just 0, so that was an easy one. Okay, so we did all of that to try to find the sum of this table. That's really what we needed. So if you do the sum of the table, in other words, the sum of this column right here, okay, so I'm going to circle that. What you really, really want, kind of like when we first learned standard deviation, is you really want the sum of these guys. So these were just organizational to get to this column right here. And so the sum that I got was this. All right, so let's plug that in the formula. We're almost there. So R, remember, is 1 over n minus 1, and then times the sum of the x minus x bar over standard deviations times y minus y bar over the standard deviations. But we already did all of this, right? All of this was already found. So this is just the sum of the table. So this is approximate because we rounded that sum to begin with. But if you do 1/4 of that, you'll get 0.824. Okay. Usually we're going to do the R to 3 decimal places, which typically means your work in the table needs to have double that, or 6 digits, in order to get an accurate 3 digits. Okay, so one thing to remember that a lot of people forget. By the way, the correlation coefficient, the closer it is to 1 or -1, the closer they are correlated. In other words, it's a stronger correlation the closer you get to 1. If it's closer to -1, it means they're strong, but they're moving in the opposite direction. As one goes up, the other one goes down. But correlation is not the same as causation. In other words, just because two things are correlated does not imply that one caused the other. So I think we've talked about this in stats before this semester. But just because things happen together does not mean that one caused each other or caused the other. It just means that for whatever reason, it might be an outside source, they have some sort of relation to each other. Okay, sometimes they do have some sort of cause to each other, but we can't make that assumption. Okay, so it's kind of a nitpicky thing, but it's kind of important that you understand it. Just because they seem to change together does not mean that one caused the change to the other, and that's an important distinction. Okay, so you might have a question on the homework or two that asks you if finding a correlation coefficient is even appropriate. And so I want you to draw two scatter plots with me. Okay, try to make this look curvy. Okay, that's what I was trying to do here. I was trying to make this look kind of curved up, kind of more like a half parabola. So I know it's a little hard to see because my dots aren't super dark. So sorry about that. My dots could definitely be darker. All right, so the correlation coefficient is inappropriate in both of these cases. Trying to make some of my dots darker. The reason it's inappropriate here is because it's not linear. Remember, a correlation coefficient is only appropriate when we have a linear relationship. And then here, it looks like we have a linear relationship. This looks like pretty linear to me, but we can't have these outliers. So if there are any outliers, which there are two little dots here hanging off by themselves, right? So we can't have that. So in neither of these cases, it wouldn't be appropriate to use the correlation coefficient in either one of those. Okay, so let's talk about maybe some real life scenarios and talk about whether we think the relationship is positive or negative. Positive relationships don't necessarily mean that they both go up. It means that they both go up or down together. Negative relationships mean that they're going to go different directions from each other. So the two scenarios, if we were plotting the age of a car versus its resale value, and there's my dog Brody drinking his water again. I think I never gave him any water in his whole life the way he drinks. Okay, so the question is, as the age of a car grows, or as the age of a car goes up, so as it gets older, in other words, does its resale value go up or does its resale value go down? And notice as one goes up, the other one goes down. So this is certainly a negative relationship. Okay, if they go in opposite directions, it's a negative relationship. The next one, a person's age and the number of gray hairs they have. Okay. Notice as they get older, as the number of years go up, right, the number of gray hairs also go up. So it's not just that they're going up, it's that they're going in the same direction. So this would be positive. Okay, so let's do one final example. It's a good one. It's a pretty kind of tedious problem. So what I'm going to do is I'm going to go ahead and let you pause the video. So we're going to talk about this problem, but I don't frankly want to do a whole lot of writing that I don't need to do. And I've already done this up. Okay, so let's talk about it, and then you're going to pause the video and fill in your table. Okay, the following table represents the average price for eggs and milk for every month from January to December in 2012. Okay, so here are the 12 prices for eggs for each month. here are the 12 prices for milk. Okay, so the first thing I want you to do is create some sort of scatter plot. So before you pause, I just want to make a point. The reason I did these little jagged edges here is because I didn't want to have to start counting at $0 for the gallon of milk, nor did I want to start counting at $0 for the dozen eggs. Okay, the point being that if you were to draw this scatter plot, it is approximately linear. Okay, so go ahead and pause the video and make sure that you include 12 lines for each of the 12 months. Okay, so I want you to, for part A, compute the correlation coefficient. Notice in our scatter plots, it's linear. We don't have any outliers, so it's appropriate to compute the correlation coefficient. Okay, before we can do that, though, we need our 4 values. We need our x bar, okay, which will be the sum of the eggs cost, because we made eggs x, and then divided by 12. Okay, so if you work all of that out, you'll get 22.05 over 12, which is not rounded, but exactly 1.8375. So we'll do the same for y, but y is going to be the sum of the milk cost, and then divided by 12. Okay, easy enough to find those. Standard deviation is a little tougher. So it's going to be first month for eggs minus the average for eggs squared plus next price for eggs minus the average squared plus so on and so forth. And then over n minus 1, take the standard deviation. So this is what you should get for milk. It's going to look like this. It's really, really important that you get your standard deviations and your means right. It really, really sucks to do all that work for nothing. So you're just going to want to be pretty careful. Okay, so again, I don't want to write all this out because I've already done it. So here's the chart that I want you to pause. Okay, notice we listed all our x values, all our y values. We did our x minus x bar over standard deviation, same with the y, and then we did the sum. Okay, so I want you to pause that chart and maybe just finish off part A. Okay, so finish off the chart. Definitely make sure you write all that out. I know it's tedious. All right, but then if we want to do R, we do 1 over n minus 1 times the sum of the numbers in this column, which ended up being 9.290105. So the correlation coefficient is 0.85. All right, so I put the chart there, so I just didn't want to write it again. All right, so now that we know that the correlation coefficient after we paused the video was 0.85, I want to ask you a couple of questions and see if you can answer. So in a month where the price of eggs is below average, the question is, would you expect the price of milk to be above or below average. Okay, so notice the correlation coefficient was positive, right? It was pretty strong positive. So 0.845 is what we have. So since we have a positive correlation, it means that they go together. In other words, as one goes up, the other one goes up, and as one goes down, the other one goes down. So that means if there's a below average month for eggs, then milk is probably also below average. Okay, so again, remember, positive correlation doesn't always mean they're both positive or they're both going up. It just means they're going in the same direction. And then lastly, can you make any conclusion about the price of eggs and the price of milk? So here's what we said earlier. The changes in the price of eggs or milk do not cause changes in the price of the other. So it's not because of the high or low price of the eggs that the milk is also high or low, but it just indicates that they tend to move together. So think of them on kind of parallel paths. They don't really affect each other, but they do tend to move together. So it might be some outside force that is causing them to go up. Maybe people's demand for breakfast or something. Okay, so I know this is a little tedious, but I know you can do it. Just set up your charts.